In the last class, we had proved theorem 2.7, which was a characterization of a cut vertex in a tree. So, a vertex inside a tree is a cut vertex if and only if that vertex is having its degree strictly greater than 1. So we proved it as in three cases: when degree of v is equal to 0, when degree of v is equal to 1, and then when degree of v is strictly greater than 1. We proved that when degree of v is equal to 0 or 1, that v will not be a cut vertex, and for the last case, when degree of v is strictly greater than 1, we proved that it is the vertex V is indeed a cut vertex of G. That's how we ended up with theorem 2.7. And now we are going to see corollary 2.7, which has the statement that every non-trivial loopless connected graph has at least two vertices that are not cut vertices. So to prove this statement, we are assuming from the hypothesis that let G be a non-trivial loopless connected graph. Okay. And already we had proved in corollary 2.4.1 that every connected graph will definitely have a spanning tree T. And here also this G will have a spanning tree, call it T. And by corollary 2.2, we have that any tree, when considered, will have at least two vertices which will have degree strictly greater than 1. Okay. And from the theorem which we mentioned now, we know that any vertex which is having degree strictly greater than 1 will not be a cut vertex for a tree. Okay. Combining those two results, we get that the spanning tree T will have at least two vertices that are not cut vertices. Okay. And among those cut vertices, we are taking suppose VB, a vertex which is satisfying this property. Okay. So what do we need? We need that G has at least two vertices that are not cut vertices. We obtained now that T has at least two vertices that are not cut vertices. So we are, as we move forward, we need to show that G has at least two vertices that are not cut vertices. For that, we are taking a particular V which satisfies this property, and since that V is not a cut vertex, we know that the number of connected components of T minus V is equal to the number of connected components of T, which is equal to 1 since T is connected. And also we know that T is a spanning subgraph of G, and definitely we can say that T minus V is a spanning subgraph of G minus V. Why? Because already T is spanning, so the set of all vertices of T will be equal to the set of all vertices of G, since T is spanning, and we are just removing one vertex V from both of them. So again the vertex set will be the same. Okay, that is here you'll have vertex set of T minus V will be equal to the vertex set of G minus V. So that means T minus V is a spanning subgraph of G minus V again. And since G minus V will have more number of edges than T minus V, and also that since G has more number of edges than T, when one vertex is removed from G and that vertex is also removed from T, the possibility of forming more connected components is for T minus T. When T from T, if we are removing V, there is more chances of disconnection. So from that logic, you can say that the number of components of G minus V will be less than or equal to number of components of T minus V. And also we already got that number of components of T minus V is equal to 1. So you have that. And also number of components of G minus V is not equal to 0 because we have chosen non-trivial graph. So the only possibility is that the number of components of G minus V is equal to 1. That means The such a vertex which we have chosen is not a cut vertex, and we know that there are at least two vertices for T which are not cut vertices. So we can conclude that G is also having at least two vertices which are not cut vertices. That's how we end up corollary 2.7. And when we move to the section 2.4, which is titled Cayley's formula, we need some basic simple definitions for that. The first definition is an edge E of a graph G is said to be contracted if the edge is deleted and its n vertices are identified together. And the resultant graph is denoted as G dot E. So to get a good picture of what is happening in an example, suppose if this is the graph and this is our E, okay, we are going to form G dot E. So for that, first we remove this, first we remove the graph, this edge completely. We are removing this, and then what you do is combine both of these edges, both of these end vertices to be one. Okay, that's how it is joined here. And the rest of the edges will come like that, and that's how we denote G dot E, and that's how the resultant graph will come. And we can also think about the number of vertices of G dot E, because we are just losing one edge. That will mean the number of edges of G dot E is equal to number of edges of G minus 1. And also for number of vertices, because we are just losing one vertex, and also for the number of edges we are just losing one edge. That will mean number of edges of G dot E is equal to number of edges of G minus 1. And also the connectivity is not lost during this contraction process, so number of components of G dot E is nothing but the number of components of G. Okay, and also there is a note: if T is a tree, T dot E is also a tree. So that is a very good observation. And also you please note that how we notate the number of spanning trees of a graph G. That is denoted as tau of G. So the next theorem is based on how to find tau of G for a random graph. Suppose E is a link of G. So link is nothing but an edge which is not a loop. That is an edge which has distinct end vertices. Okay. So if E is a link, then tau of G, the number of spanning trees of G, is equal to the number of spanning trees of G minus E plus the number of spanning trees of G dot E. So for that, we are considering a the number of spanning trees of G that does not contain E. Okay. So for every spanning tree of G that does not contain E, the same spanning tree is also a spanning tree of G minus E. Right. So that means the number of spanning trees of G that does not contain E is nothing but the number of spanning trees of G minus E. So that is the first observation we make. So the number of spanning trees of G can be splitted as two: the number of spanning trees in G which does not have the edge E, and the number of spanning trees of G which has the edge E. It can be split up like that, split it like that. And the first section is obtained as tau of G minus E. Okay. Now to each spanning tree T of G that contains E, there corresponds a spanning tree T dot E of G dot E. So whenever you have a spanning tree T of G that has E, G dot E, the graph G dot E will have the spanning tree T dot E. And this correspondence is 1 1. Suppose if we have T dot E to be a spanning tree of G dot E, then T will be a spanning tree of G. That is our 1 1 correspondence. So Tau of G dot E is nothing but the number of spanning trees of G that contain E. So in total, we can end up with a result. So how did we do? We took the number of spanning trees of G. We need that. So we said that that is equal to the number of spanning trees of G that does not contain edge E plus the number of spanning trees of G that contain E. Right. So then we observed the first class and then we observed the second class and finally you obtained what is given in the statement, and it is a very important result and it is useful to find the number of spanning trees of a random graph G. And as an illustration, and also you can see an example given in figure 2.7 about this contraction of an edge. So here the edge is E sitting here. So the edge E is being contracted. So this edge is removed and this vertex are joined together, and finally what you get is G dot E, which is the graph, resultant graph. So to use a theorem 2.8 to give an illustration, what you're doing is you're going to do the induction process for a graph sitting here. This is a graph. Okay, we are going to find the number of spanning trees of this graph. Okay, for that, what you first do is suppose this is our edge E. Okay, so what you do is first you remove the edge. Okay, so form the graph there, plus you join the edges, you join the end vertices, right? Okay, so now you are having two graphs. Now think this is E. Okay, remove that E. We are considering this graph first, this graph. So you removed it, okay, and then you joined it. So that is what you're doing is G minus E, G dot E. This is the process. So you made it like that. Now you think about the second graph. So it is being splitted like this in the second step. So here suppose if this is E, so you're removing this E, so you get G, uh, the first G minus E as this, and then adjoin this vertex to this vertex by removing this E, so you get this. Okay, now if this is E, so you have now four graphs, right? So for this graph, you know that it is connected. Suppose if we choose any graph, any edge from this, and if you're removing that edge, you get a disconnected graph. We can't use disconnected graphs. So once you have got a connected graph and when you're trying to split it up, suppose if it is going to show you a disconnected graph, you leave it. So you're going to leave this graph as such. Now take the second graph. Okay, suppose choose this as E, then this will be G minus E, and then join both of them together, the n vertices together, you get the vertex, the graph here. And then for this graph, split it up, you choose this as E, remove it, and then adjoin it together, so you get the graphs here. And for this graph, choose E, and then adjoin it together to get this. Okay, so you obtained this much graph. So you keep this graph as the same, and for this graph also, if you're removing an edge, you are ending up with a disconnection, so you keep it like that. Now for this graph, choose this to be E, and you get this, and then you join together n vertices to get this. Okay, from this graph, you are getting these two. Okay, and for this, if you are removing any edge, you will get disconnection. So you are not removing, you are keeping it as this as the same. And for here also, if you are choosing one of the edges, suppose if you are choosing this edge, then if you're choosing G minus E, you'll get a disconnection. So you keep it like that. You are not uh, changing it. Here also, you are not changing, because if we are choosing the edge to be this edge, then there will be a disconnection possible. So you keep it like that. And for this, suppose if you are choosing this edge, okay, uh, and you are removing the edge and then again adjoining, because the vertex is the n vertices is the same. So if you are adjoining, you get the same graph twice, that is g minus e and g dot e will be the same for this graph. So you are not pushing it further. And and using the same idea, you cannot do anything for these graphs again by splitting them into g minus c and g dot e. So how many graphs you obtained? 1 2 3 4 5 6 7 8. So that will be the number of spanning trees of the graph G. But these are not the spanning trees, we just used them to find the number of spanning trees. Each graph represents the number. They are not the spanning trees, they are the number of spanning trees of the graph G. And the next theorem is based on finding the number of spanning trees of a complete graph on n vertices kn, which is equal to n raised to n minus 2, which is associated with Proofer's chord. It is a proof given by Proofer. So that we will do in the next lecture. So thank you.